Hello everyone, and welcome to this Open Day Taster Lecture from the Department of Engineering Science at the University of Oxford. My name is Amy Zavatsky. I'm a reader in Engineering Science and a tutorial fellow at St Edmund Hall. Today I'd like to give you an introduction to the analysis and modelling of human body movement. After a brief introduction to the engineering approach to problem solving, we'll look at three areas of human body movement: mass, center of mass, and moment of inertia, path of motion and position as a function of time, and briefly, work and energy. As you know, engineering is the application of mathematics and scientific principles to solve practical problems. We ask the question, how can we solve a problem within certain constraints? These may be time, money, space, weather conditions, or properties of materials. So we have a problem that we solve within constraints. And to do this, we have to undertake some analysis and then to do some design. And in doing so, we use models. Now, a model is a simplified, often mathematical description of a system to assist calculations and predictions. In modeling the motion of a body, we create a model of that body, and the simplest model is a particle. So this is an object which has a mass, but no size or shape, so it's just a dot. We can also have systems of particles. As an example, on the right, we have two dancers, and if we're not worried about the details of their limb motions, then we can represent each of them as simply a particle moving around in space. Now we can also study the motion of bodies. And a body is a system of connected particles. These can be connected rigidly, or they can be allowed to deform. And we can also have systems of bodies. The bodies can be independent, or they can be linked. So as an example, let's look at the dancer in the photo on the right. And we could represent him as a system of bodies. And let's say that they're rigid, so we have a segment or body representing the head, one or two for the torso, the upper arm, the lower arm and the hand, the pelvis, the thigh, the lower leg or the shank, and the foot. So that's a little bit more complicated than just representing the body as a particle. Well, what do we do if we have a rather complicated system of bodies? Well, the model that we choose will depend on the question that we're asking. So we could choose to represent each body as simply a particle, and the particles moving relative to each other, or we could represent the bodies in terms of links of segments, and then all of these would again be linked together to represent the dancers. So it could be quite a simple model, or it could become really rather complicated. Now, if we're thinking about body movement, we have to look at the equations of motion. So let's have a brief overview of these. Everyone will know of Newton's laws of motion, and the second law is written here. That says that the sum of the forces, the external forces applied to a particle or body, is equal to the rate of change of linear momentum. Linear momentum is the mass times the velocity. This is also equal to the mass of the body or particle times its acceleration. So we see that the mass is the body's resistance to being accelerated. This takes care of linear motion, but in order to cover angular motion, we have to look at a separate equation, which was formulated by Euler. This says that the sum of the external moments on a body is equal to the rate of change of the angular momentum. So for Newton, we had forces, and for Euler, we have moments. And the moments are the turning effects of the forces. So the forces that cause a body to rotate. And on the right-hand side, we had the rate of change of linear momentum, and down at the bottom, we have the rate of change of the angular momentum. Now, this right-hand side of the equation can take a number of different forms, and I've written out one of these on the right, just for illustration. So this has within it some terms that are related to the angular acceleration of the body and the angular velocity of the body. So that is how fast the body is spinning or turning. And it also has terms which are the moments of inertia. So these are the equivalent of mass in Newton's second law. So the moments of inertia are the resistance the body has to being turned or spun. So let's have a look at mass, center of mass, and moments of inertia in more detail and see how those are applied in studying human body motion. We define the mass of a body as the sum or the integral of all the little masses or particles of the body. So the integral of dm is equal to the total mass. We define the center of mass of a body as the weighted average of all the positions R of all the mass particles of the body. So R here is a vector. It is a quantity that tells us the distance of the mass from a particular point. So we sum all this up for all the body particles and then divide through by the overall mass. And we get the position of the center of mass. So this would have x, y, and z coordinates. We define the moment of inertia in a similar sort of way, except here we're having this r, this distance squared, times the little dm's, the particles of mass. And this r is the distance of dm from the axis of rotation about which we're concerned. So we sum up all this for the whole body, and that then equals I, the moment of inertia about a particular axis. Now, in engineering, we can calculate these quantities for various objects. But once we've done that, we don't want to have to do it again, so we compile these values in tables, or these formulae in tables. So these are some examples from engineering tables and data that our undergraduates use. So you see here, there's the body coordinate system, and then we have the surface area, the volume, the location of the center of mass in X, Y, and Z coordinates, and then what we call the principal moments of inertia about the X, the Y, and the Z axes. So in these formulae, we have the mass, and then we have things to do with the geometry, the length down here, the radius, and the height of the cylinder. And the point C here is the center of mass. Let's look at two other objects in our table. We have a uniform hoop and the arc of a hoop. So the position of the center of mass here depends on the radius A, and for the arc, it depends on this angle theta. And what I'd like you to note for the last two objects is that the center of mass is not actually on the body. So here it's in the center of the hoop, and here it's actually outside the arc of the hoop. And we'll come back to this in a few slides. For human bodies, we can also look up values for weight and moment of inertia in tables. And these are called anthropometric tables. So anthro means man and metric means measure. So they're measurements of people compiled in tables. And this table shows the body segment parameters for the leg. So we have a column here which says what the segment is, its definition, the segment weight divided by body weight, that's overall body weight, and then the location of the center of mass relative to the upper and lower ends of the segment, and something called the radius of gyration. And this relates to the moment of inertia. So radius of gyration is k. So if we take k squared times the mass, we get the moment of inertia. So as an example, let's look at the thigh segment. So it's defined as being from near the hip joint to down near the knee joint. Its weight is 10% of body weight. Its center of mass is 43% from the top end. So coming down from the top or the proximal end, 43% we get to the center of mass. And then we can have the radius of gyration and moment of inertia relative to the center of gravity or the center of mass, and relative to either end, proximal or distal. So this gives us a kind of general feel for the body segment parameters for a particular person. That, of course, is in 2 dimensions. We can also work these things out in 3 dimensions. And for that, We could model the body as being composed of ellipsoids, spheres, cylinders, and so on, rather like the artist's mannequin. And we can go to our engineering tables and look up what the centers of mass are and what the moments of inertia are for these shapes. If we want something more detailed, then we could go and do some 3D body scans and do person-specific calculations for the parameters, or we could possibly do some medical imaging and work out the parameters from that. So this is the image of a foot from the side. Here's the heel, and here are the toes. This is a CT scan. Of course, scanning is much more expensive than looking up something in a table. So as a first guess, first working through of a problem, we would tend to use the values from tables and see how far that gets us in understanding our system. So the human body's center of mass, the overall center of mass, is the weighted average of the locations of the centers of mass of all the individual body segments. So when a person is standing upright with good posture, the body's center of mass is around the level of the top of the hips, so the waistband of this man's shorts. And for good posture, we see that the segments are pretty much all stacked one above the other. And their line falls within what we call the base of support of the person, so under his feet. In this position, the body has to do very little work. The muscles are quiet and just hold the body if it starts to sway forward and backward or side to side. So good posture is actually a very low energy state for the body. Here's an example of how the center of mass has to be kept above the base of support of the body for stability. And this is from a study where we have a soldier carrying increasing amounts of load. So on the left, he's carrying a small amount of load in his hands, and his center of mass and everything is lined up to be above his feet. So very similar to the image on the left. Adding a small amount of weight on the front and back doesn't do much to his posture. He is able to stay upright. But when a backpack is worn, you can see that he started to have to lean forward. So his head is moved forward of this line so that he can keep his center of mass above his base of support. And when even more weight is added to the backpack, you can see that he's had to incline himself quite far forward, again, to keep his center of mass above his feet so that he doesn't fall over. So by changing the distribution of body segment masses, we can change where the center of mass is. Let's look at that in a little bit more detail and look at the example of the high jump. So I want you to think about where is the center of mass of the athlete's body in relation to the bar. So here are some images of the different techniques that have been used over the past 100 years or so to do the high jump. From 1928 down to about 1968 here, and present technique. I think it's safe to say that in these four techniques, the center of mass is approximately at the yellow circle position, and we can see that it's clearly above the bar when the person is clearing the jump. Now, for the last technique, called the Fosbury flop, I want you to think and to remember the arc of the hoop that we had and where the center of mass was relative to that. Let's flip that by 90 degrees and compare that to the high jumper here. So he's put his body into the shape of an arc. The center of mass of the arc is somewhere down here. So we see that to clear the bar, he hasn't had to raise his center of mass as high as these athletes using the other techniques. And in fact, if he arches his body enough, that center of mass can actually pass under the bar. So by doing this, he's doing less work to raise his center of mass, but still clears the bar. There are some very good illustrations and videos of these techniques online. So if you look up the Olympics, Amsterdam 1928, all the way through Berlin 1936. 1968 was when Fosbury introduced this technique, and you can look at his technique compared to current techniques looking at, say, the London Olympics. And Fosbury was, in fact, an engineer, which is interesting. Okay, so we can look at the body's center of mass. We can also look at the moments of inertia. And I said that these are this is the resistance to being rotated about an axis. So here, let's think about how far from the axis of rotation are the body segments. So on the left, here we have a gymnast who's spinning about a vertical axis. All his body segments are quite near to the axis, and so his relative moment of inertia, let's say, is 1. Moving along, he then puts his arms out to the side as he's spinning, so his mass is further away from the axis, and his moment of inertia has increased to 2, so it's doubled. In the next figure, he's in a tucked position, spinning about a horizontal axis. In this case, the moment of inertia is 4. In the next figure, he's now flat out, as he might be in a dive or in spinning around a bar in a gymnastics exercise, and his relative moment of inertia is now 12. And at the far end, spinning about a bar with the arms extended increases that moment of inertia to 76 times what it was in spinning around a vertical axis at the left. So you can see how by moving our body segments, we can change our resistance to turning or spinning. This is also linked to the speed at which the body spins. So here we have a diver. So he starts out in an extended position, goes into tuck, and then extends out again. And this graph shows H which is his angular momentum, I, the moment of inertia, and omega, his angular velocity or his spinning velocity. Since there are no external moments on him, it's just gravity acting through his center of mass, this angular momentum h is a constant. So if we change I, then omega will change. So we know that when the body is flat out here, spinning about an axis through the middle, I is relatively high. During the tuck, I is at a lower value, and then extending the body out, I increases again. To keep h constant, omega has to change. So it starts out at a low rate of spinning. When the diver is tucked, he's spinning quite fast. And then as he extends the body out, his rate of spin slows down. So by changing his I in the dive, he's changed also the omega. Okay, well let's now have a look at the path of body motion and its position as a function of time. So I'd like to show a video here of a person doing some back flips, and the motion of the person was measured in a motion capture laboratory by putting some markers, these little balls, on the skin. And then there's a model of the body which is represented by this skeleton, and you'll see it moving around. And there are no hands and no head because those segments weren't tracked. The blue dot is the body's center of mass. You can see in the arched position here that center of mass is outside the body, as we saw for the high jump. And this white line is the trajectory or the path of that center of mass. So let's have a look at how that moves. So you can see when the body's straight, the center of mass is round about the pelvis, and then when the body is arched, it's outside. We see that again from a slightly different angle. Okay, so we can ask questions about this motion. Once we've tracked it, we can say, does the center of mass take a direct or an indirect path from point A to point B? Is that path straight or curved? Is it cyclic? Is it repeatable? We could ask, how smooth is the path? Is it a nice fluid motion that the body has taken, or does it change abruptly? Is it a jerky motion? And we can quantify these things. So we can use motion capture to work out the path of motion of the body and the trajectory of the body's center of mass. We can also look at the position of the body and its center of mass as a function of time. So this is an example of sprinting. This is Usain Bolt. On the left, he is in the starting blocks. In the middle, just after the start. And on the right, near the finish. Below, we have the speed-time graph for a typical sprinter. So the sprinter starts at zero velocity, zero speed, and accelerates, so increases speed. At some point, reaches the maximum speed, or maximal velocity and stays at that for a short period, and then towards the end of the race there's a tendency to slow down. On the right here, we have a graph of the data collected, or Bolt's actual speed. This is speed versus distance rather than time, but it ends up being quite a similar graph. So we start at zero speed. Speed is increasing rapidly, so there's an acceleration, continued acceleration, nearly reaching a constant speed, constant velocity up at the top here, and then a slight slowing down towards the end. So we can worry here only about the position of the sprinter's center of mass and see how he moves, but we could also then start to use motion capture, say, to worry about the positions of the body segments, the angles of the joints, where are the arm positions, how do they compare for the different runners, and so on. Now finally, a brief word about work and energy. Now when we study physics and engineering, we tend to think about mechanical work. So I'll use as my example here a person going upstairs. On the left we have a person in the lab, which is just, he's walking up some stairs to a height h. And on the right we have a woman on a stepper machine in the gym. So she's moving her legs and going up and down, but she's pretty much just staying at the same height on the machine because the stairs are what's moving. So how much work do these two people do? Well, the mechanical work is the external work done, and this is done against gravity. So it's equal to simply the mass of the body times the acceleration due to gravity times the height, so mgh. So as the man moves from floor level to a height h, he does work of mgh. On the right, the work done against gravity is approximately zero, because the person doesn't go up and down, she stays at the same height. Now this may seem strange, because if anyone has ever used these machines, you know that you do an awful lot of work to move your body against the stairs and the resistance of the stairs. But that's not external work. That's what we call internal work. So that internal work is the work done by the muscles in flexing and extending the joints. So here, although we have zero external work, we'd have quite a lot of internal work. And to estimate this internal work, we would need some sort of biomechanical model. So something like you see in the image on the right. The red lines here represent the muscles, and if we know the body motion, we can calculate the lengths of the muscles and the speed at which they contract, and then we could work out how much work the muscles are doing. Alternatively, we could use some sort of oxygen consumption equipment to measure what's called VO2 or VO2 max. And you may well have seen images or videos of somebody walking along a treadmill wearing a face mask, and that face mask is measuring the composition of the air that's being expelled from the lungs, and from that we can make an estimate of the oxygen that's been consumed, and hence how much work the body is doing. So in this short lecture, I hope I've given you a little introduction to the engineering approach to problem solving and using models, and how those models, particles and bodies, are used to study human body movement. And we've had a look at the mass, the center of mass, moments of inertia, the path of body motion and position as a function of time, and a little bit about work and energy. So I'll just thank you very much for your attention and say that I hope you will be able to visit Oxford sometime in the future. Thank you.